Hello everyone, welcome to my YouTube channel School of Chemistry. Today we are going to study about acidity of alcohols and phenols. We are going to study about the acidic nature of alcohols and phenol. Now alcohols react with a lot of metals, like they react with the sodium metal, aluminium, magnesium, alkaline earth metals to evolve hydrogen gas. Let us take few examples. That we can write down the reaction of ethanol CH3 CH2OH with sodium metal. So for that we have to take two molecules of ethanol. When it's going to react with the sodium metal, it leads to the formation of sodium ethoxide O negative Na positive sodium ethoxide with the evolution of hydrogen gas. And if we have the aluminium metal, we can take the tertiary alcohol. As the reactivity of alcohol increases with the primary, secondary and tertiary. So if we take a tertiary alcohol, it's reactive with more. So we'll be taking two aluminium atoms, reacting it with this 2-methyl propane 2-ol, and we are getting O negative, and this should be whole thrice and aluminium, and 2 over here plus 3H2. Similarly, phenols also react with the sodium metal to evolve hydrogen gas, that shows the acidic nature of phenol. So if we react with sodium metal, use two molecules of phenol, it leads to the formation of two molecules of sodium phenoxide O negative Na positive plus H2 gas. Similar type of reaction is shown by phenol when it reacts with a strong base like sodium hydroxide. So also in that case, phenol reacts with sodium hydroxide to form sodium phenoxide with the formation of water. So this is the salt plus the formation of water. This one is sodium phenoxide. So these reactions shows the acidic nature of alcohol and phenol. Let us compare the three types of alcohol, that is primary, secondary and tertiary alcohol, in their acidic strength, that how we can compare the three types of alcohol. So we have ROH as the 1 degree alcohol. We can write down RCHOH, and we can put an R over here. This one is the secondary alcohol, and three alkyl groups attached to a carbon atom. This could be written as a 3 degree tertiary alcohol. So we can say that when these are going to react with the metal, hydrogen will be evolved. They act as a Bronsted acid. Bronsted acids are those acids which give you H plus ion. Okay, so lead to the formation of RO negative alkoxide ion, RCHRO negative ion, and over here in the tertiary alcohol it leads to the formation of RCRO negative ion. As we know, this alkoxide ion is an electron donating species or electron donating in nature. So it's going to donate its excess electron density to this oxygen, making it less stable. Okay, over here we are having two alkoxide ion donating its electron density to the carbon, which is further donating its electron density to the oxygen atom, making it more unstable. And in the tertiary alcohol, three of the alkyl groups are present, which will be donating their electron density to the carbon, which will be transferring its electron density to the oxygen, making it least stable. So as we can see over here, that primary alkoxide ion is the most stable and the tertiary alkoxide ion is the least stable. So we can say that the primary alcohol are the most acidic. So the acidic nature of alcohols follows the order as 1 degree is more acidic than 2 degree is more acidic than 3 degree. This is the order which is usually followed by the different alcohol, that is primary, secondary and tertiary in their acidic strength. If we compare alcohol to that of the water, that which one is more acidic, whether water is more acidic or alcohol is more acidic. So in case of alcohol, the dissociation can be shown as RCH2OH. Okay, so it's dissociate as RCH2O negative plus H positive. Fine. And in case of water, we can write HOH and it's dissociate as O negative plus H positive. As we can see, in the alkoxide ion, the oxygen atom is attached to an alkyl group, which is electron donating, which increases the electron density on the oxygen atom, making it less stable. But hydrogen doesn't have any excess electron density on it, so doesn't provide any excess electron density to this oxygen atom, so making it more stable. So this shows that your hydroxide ion is more stable as compared to the alkoxide ion, stating that water is more acidic than alcohol. Now one more evidence we get for this statement, that when we react alkoxide ion with water, that RO negative, if it's react with water, this lead to the formation of ROH plus OH negative, stating that reaction is not reversible. This reaction is not reversible. If the reaction is not reversible, it shows that water can give its H plus ion to an alkoxide ion, but an alcohol molecule cannot donate its H plus ion to the hydroxide ion, so making water more acidic as compared to alcohol. Now let us talk about the acidity of phenol. If we compare phenol to that of alcohols and water, they are said to be as more acidic than alcohols and water. Why so? As we can see over here, that in phenoxide, the dissociation of phenol can be shown as O negative and plus H plus. Now this, the carbon of the benzene ring, they are sp2 hybridized. All the carbon are sp2 hybridized. So this benzene ring act as an electron withdrawing group, which withdraws the excess electron density present on the oxygen atom and making the OH bond weaker and making the dissociation of H plus ion more visible. So that's why the phenoxide ion is more stable as compared to phenol, and that can be even illustrated by drawing the resonating structures of both the molecules, that is phenol as well as phenoxide ion. Let us draw the resonating structure for phenol as well as for phenoxide ion. So when we draw the resonating structures for phenol, we can draw the resonating structures for phenol like this, that delocalization of the charge or the lone pair present on the oxygen. So in this, oxygen atom develops a positive charge and the negative charge is delocalized on the benzene ring. So this get inside, forming a double bond. Negative charge comes at the para position. This bond will remain as it is. Oxygen, hydrogen will remain as it is. One lone pair and positive charge. In the next structure, this gets inside. It comes at the ortho position. So we can draw the next structure as double bond over here. Next double bond comes over here. Negative charge comes over here. Single bond with the oxygen, hydrogen, one lone pair and a positive charge. Now this get inside over here. Okay, there should be a double bond over here between oxygen and hydrogen. So when it gets inside, this gets back. So this forms OH again. So as we can see, in three of the structures of the phenol, there is a positive charge. In structure second, third and fourth, there is a positive charge on the oxygen atom, which is more electronegative, and a negative charge present on the carbon atom, which is less electronegative, making it less stable. And if we look at the resonating structures of phenoxide ion, let me draw oxygen with three lone pairs and a negative charge. So I will be drawing the resonating structures for this oxygen phenoxide ion. It comes at the para position. Oxygen double bond over here, negative charge at the para, get inside, and the double bond comes at the ortho, or the electrons of the double bond comes at the ortho position. This bond get formed, negative charge over here, oxygen 2 lone pair, this electron get inside and they come back to the oxygen. So when we are going to look at the resonating structures of phenoxide ion, then there is only a negative charge present either on the oxygen atom or on the carbon atom. There is no charge separation that takes place in the phenoxide ion, but there is charge separation which is taking place in the phenol, making it less stable as compared to phenoxide ion. That's why this phenol dissociates quickly to give H plus ion to form more stable phenoxide ion. If we compare phenol to that of ethanol, so ethanol RCH2 or any alcohol, I can say primary alcohol RCH2OH, ethanol could be CH3CH2OH. So the dissociation can be shown as RCH2O negative plus H positive, and this structure is not resonance stabilized. Whereas in case of phenol, the phenoxide ion formed, this is phenol, the dissociation, we show it as O negative plus H positive. The structure formed over here, this is resonance stabilized. So the phenoxide ion is resonance stabilized, whereas alkoxide ion is not resonance stabilized. So we can say that phenol is more acidic as compared to normal alcohols. One more thing, if we add any electron withdrawing or electron donating group to the phenol, what will be the effect of? Will be the effect of attaching an electron withdrawing group or electron donating group to the phenol on its acidic strength. As we can see that if electron withdrawing group and electron donating groups are present at the ortho and para position, then only they can benefit into the acidic strength, or they can decrease or increase the acidic strength of phenol. So if an electron withdrawing group is present, we can say suppose this is phenol and this electron withdrawing group is attached on phenol at ortho and para positions, at ortho and para positions, then it's going to stabilize this phenoxide ion. Then it will be stabilizing the phenoxide ion making it more acidic. But if any electron donating group is present at ortho and para positions, like methoxy group is present, okay, methyl group is present at electron donating group at ortho and para positions, will decrease the acidic strength of phenol as it's not going to stabilize the phenoxide ion, as the stability of phenoxide ion will be decreased. Ion will be decreased. Okay, that's all about the acidic nature of alcohol and phenol. Okay, let us quickly recapitulate it. So we have started with the acidity of alcohol and phenol, that alcohols are acidic in nature. They act as a Bronsted acid, as they can give H plus ion, and this can be proved by their reactions with metals like sodium, aluminium, magnesium. Okay, so they release hydrogen gas. Similarly, phenol also reacts with the sodium metal to release hydrogen gas, and even phenol reacts with sodium hydroxide, which is our strong base alkali, to produce sodium phenoxide, which is salt plus water. If we compare the acidic nature of primary, secondary, and tertiary alcohol, then primary alcohol is the most acidic, and tertiary alcohol is the least acidic. That is due to the stability of the alkoxide ion form. Then we have compared alcohol with that of water, that which is more acidic, alcohol or water. So we have first compare alkoxide ion with the hydroxide ion. That alkoxide ion is less stable as compared to hydroxide ion due to electron releasing nature of the alkyl group. And the reaction of alkoxide ion with water forms alcohol with hydroxide ion, and the reaction is not reversible, stating that water are more acidic than alcohol. Then we have discussed about the acidity of phenol. That phenol dissociates from phenoxide ion plus H plus ion. And when we are going to draw the resonating structure for phenol and phenoxide ion, we can see from the resonating structure that there is a charge separation. In case of phenol, that the positive charge comes in three of the structures on more electronegative oxygen atom, and the negative charge is delocalized on the less electronegative carbon atom, making phenol less stable as compared to the phenoxide ion, in which the negative charge is delocalized on more electronegative oxygen atom in two of the structures and less electronegative carbon atom in three structures, and there is no charge separation. Then we have compared alcohol with that of the phenol, that which is more acidic, alcohol or phenol. Alcohols are supposed to be less acidic as compared to phenol because the alkoxide ion is not resonance stabilized, whereas our phenoxide ion is resonance stabilized, making phenols more acidic than alcohol. Now, what will be the effect of attaching an electron withdrawing or donating group on the acidic strength of phenol? Whenever we are going to attach an electron withdrawing group at ortho and para position, that's going to increase the acidic strength of phenol. And whenever an electron donating group is present at ortho and para position, that will definitely going to decrease the acidic strength of phenol, because the electron withdrawing group will withdraw the electron density of the OH bond, making it less stable, whereas the electron releasing group will donate the excess electron density on the oxygen atom, uh, increasing the strength of the OH bond. Hope my videos are helping you in your studies. So for more interesting videos, please like and subscribe to my YouTube channel, School of Chemistry.